I'm gonna start here. Um, okay. So, um, we did go through this part earlier in a previous lesson. Um, but we were looking at just some very beginner basic stuff with Haskell. I purposely imported, or sorry, I added this no implicit prelude, just to show you guys like kind of basic modules that we're working with in this file. Um, and it ultimately, if we didn't have this, then we wouldn't need to import any of these. But again, just to show you guys what we're working with. Um, and we didn't. We this was our agenda. We never really got through it all. We talked about common interview questions, how they evaluate, how any Haskell expression evaluates, um, and how lambda calculus makes everything a first class value. I'm not even sure we got that far. I think we literally just talked about how they evaluate, which I'm going to go over again today. But then we got to working with structure, or sorry, then we'll get to working with structure, and then how to ignore that structure and how to do some more advanced advanced things in Haskell, and why this structure is important, um, and we'll see what I mean by structure. Um, so yeah, where did we go? This is all just from last time talking about this. So we have a very simple function here. Is palindrome. Can I zoom in on this? How do I zoom in on? There we go. So yeah, is palindrome um, is kind of our simplest example of a function. So there's really like only so many parts to a function, and all of our syntax in Haskell ultimately boils down to this and a few data type declarations. We of course have our function name. We have this kind of symbol to say this name is of the type that follows. Um, and then we have, of course, that type. So this type tells us here that this is a function which takes a string as an argument, and this will give us back a bool. We know that it gives back a bool because it's the this is actually just a type itself, and we know that the type right. So we can kind of even show this here. This is just a type itself, and this makes sense. And this is going to make intuitive sense that a type is just something which takes an as an input and takes an output. Or sorry, takes an input and gives it back some result. And that's all this is really telling us. So we know that this B is the output that we're going to get back. I can even rename this if I want. Um, and now that we have this data declaration, we actually have almost all of the Haskell syntax that we would ever need to learn to become, you know, like experts in Haskell. We have most of it right here. Um, yeah, and so that's the type of our function. We can see that it takes. Sorry, we can see the next part here. This highlighted region is referred to as the head of the function. And so, what is important to note here is that this um, this is binded to the type of string. Like this variable is going to be of the type string according to our function. Um, and then yeah, so the last part is our expression. So just like how in the type, um, the type of the function we see that on the left side of the arrow we have a string, and on the right side we have a bool that we return. We can see that on the left side of the equals we have a string, and on the right side we have what is a bool expression. Right? This is not literally a bool, right? I'm not literally typing out here true, because why would I ever do that? Our functions, um, we use functions to um, to check the result of something, to see ultimately what the answer is, or to ask a question about something. And so, for example, here we are asking the question of, is this a palindrome? Is this string a palindrome? And in order to do that, we're going to need to write an expression, so that we can, ask this question again and again, right? We want to create an expression that's going to work with any word, to see if it's a palindrome, and hence why we need an expression. Um, the only restriction that we have for this section of our overall function is that it returns the proper type. So we are free to go nuts with whatever Haskell, um, Haskell logic we want to. Um, for example, I could do something like silly, like I could say, and true, um, which does nothing. It actually does nothing. I can continue to, tack these on.
If you said at false or and false though, it would change the.
Yes. Yeah,
I don't
exactly.
know if that's what you were trying to show or.
No,
But never.
you're right. No, I guess so.
I guess that's yeah. Sorry. Continue
All
on.
good, all good. I guess I'm trying to say, like, these do nothing. You're like, so yeah, like, your point about the false doing something. I couldn't then, as soon as I guess I say this, that does change it. But
Yeah, so now it's only gonna. You're basically just nodding
yeah,
that whole expression.
yeah,
But
yeah.
anyways,
But what we're trying to do is, like, build up an expression that does the same thing. I guess, like, we want to return the same result, but have different expressions. I guess
yeah, I see what you're saying.
there's
Yeah, I
this
see
is
what you're
only,
saying. Yeah.
yeah, this is only really like tiny side point here or whatever. All I'm really saying is that this Haskell expression can become infinitely complex, and so I'm just kind of picking those branches of infinite complexity that we can see don't do anything. Right? So even if I add this in, this is still going to return the same result of whatever this is. But I'm getting a little sidetracked there. All I'm really saying, is that we have free reign over our expressions. Right? And we keep that in. Um, this is valid because this entire expression is going to result in a bool or a boolean in other languages. And that is our only restriction. So, right, and if we further evaluate this out, right, like if we were to kind of take this and say, what is the next step here? We would see that we, like, reverse the string, right? So if we know our string is ABBA, the band, I guess, because they're easy to use here, we can see that ABBA is the reverse. We check if ABBA is the reverse of ABBA. Um, we then see what the reverse of ABBA is, and we check to see that it is in fact ABBA, which then means that we are going to run ABBA, is ABBA equal to ABBA for the input of ABBA, and we see that is in fact true. So we see that our expression gives us back a bool, um, and so our function type checks. Um, you know what? This is a bit of a deviation here, but this is how you would load the file, by the way. We can just go into GHCI, and I can just simply say load, or L for short, beginner.hs. It compiles. Okay, that's great. What that tells me is that my function is type checking, which probably means that I'm doing something that I intend to. um, what if I said something that kind of makes sense, but actually doesn't make sense? It's gonna blow up in my face. So I'm saying here that string um, is equal to false. Or actually, wait, can I do that? Sorry. Or no, this is what I mean. I guess this is what I mean. Sure, that example sounded better, but that's because it type checks. So just ignore that. Let's say I want to do this. Um, oh yeah, that's also gonna fail. This is going to give me an error. And so like if you're coming from other languages, I find that like when you're in other languages, especially like um well, I'm sure the flavor of it is just different today, but like how I would look at an error when I was, a newer developer is I would say, oh my gosh, look at this foreign language that I've never seen before. Let me copy and paste it, and I'm going to then go and try and you know try and check it on Stack Overflow. Uh, you know what? And honestly, we could do this. Like we could take this part here, and we'd probably find a Stack Overflow that tells us about this. But like um, what you'll the key point I'm trying to make here is that there's only so many errors that we really see in Haskell.
Yeah,
Um,
that was the point I was going to make. Is it's literally like by the time you've interacted with an error, you'll have memorized how to solve that error. And there's like maybe what 7 or 8 like
yeah,
that I can think of off the top of my head that are like the ones that you'll have to know how to read. And this just brings up a good point because I remember Galen, you and I were looking at a stack trace the other day from Python
yeah,
or for C sharp, and the stack trace of things that were occurring was probably like 10,000 lines
oh,
of code,
yeah,
and not one place in there did it give you like a really good hint as to what was going on.
yes, yeah, and
So with that in mind, that's where that whole like errors are scary kind of thing comes from, because in Python errors or in
they
other
are
languages
scary.
errors can be scary
Yeah,
because they're dealing with a lot of virtual memory, right? So it's like there's
yeah,
that whole extra component that Haskell doesn't have, and where an error in another language might be like a huge stack trace, this is just telling us exactly what the problem is in a certain area. And this one seems obvious because it's like a type error. But if you remember, or types are first class citizens in Haskell, so that extends into our programming logic as well.
yeah, totally. Um, yeah, and you know what? I'm gonna use a function as a type error in a second, just to show you guys like a more
Yep.
scary looking error, but
Yeah.
how it's actually not that scary. And also too, what's funny with that error that Kyle and I were looking at is that if you go like let's say the stack trace is like 20 statements deep. If you go like 10 into that stack trace, you can see this like thing called dependency injection, and then that's where this error gets really scary because like what that ultimately means is that there's not a the code was that we were working with was simple for the most part, but like at that point you kind of lose like referential transparency, and you'll have this whole class of errors that like is hard to even like pinpoint what's going wrong. So that like that's all like oop stuff. That will never happen in Haskell. Um, like this will never like that was just sorry that will never happen. This error message is so beautiful because it tells us everything we need to know. For example, that is on line 86. I can see that line 86 is where the error is. It's highlighting that's not like this is the error that or this is the value that we're talking about that we are confused by. Um, and it just says expected a string, but we actually just gave it a bool. Um, and yeah, so it's just simply a type mismatch, and all we need to do is replace it with a string, um, and voila, we are good. That would work, or of course the reverse string would also work. Let's take another function here. I'm gonna use the equals function just for like the sake of it. Um, I'm gonna say is equal to string. Yeah, equal to string is a function. Equals is equals.
Is that going to compile?
No,
Okay.
no, heck no,
Yeah, it's like what?
no.
I see what you're doing.
It's gonna be another type mismatch. Um,
Yeah.
yeah. So, um, like so equals of course, right? We see like is a function which takes. Actually, that's kind of worse. Is a function which takes two arguments and returns as a bool. So if I give it a equal to 1 and I check the type of that, I've applied one argument, and so um, I can see that it's going to take one more type to become fully applied. So that's what I've done here, and this is going to give me a type error where I have a function that is incorrect. So this is the scariest type error that you're going to get in Haskell. Um, really,
Yeah. It'll look scarier than this because there'll be different types. Maybe you're working with a library, but it ultimately all comes down to
yeah,
this exact thing.
yeah,
It might look like there's more going on, but there's not.
yeah,
Um, and this comes down to a lot of the times you've just got something that's not fully applied
right,
or not applied to the right level. That because you got to remember partial application. Certain functions rely on that idea of partial application, and they'll take other functions as functions,
right.
or they'll take in a value, but what you're giving it is a function. So you need to handle that function and then pass the value through or map
Yeah,
over it.
yeah, 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 yeah. So like we're like what Kyle's bringing up is like ultimately the idea that this parses. Um, and this is valid syntax, right? So like Haskell compiler and type checker has to be prepared to handle this valid syntax that might not type check. So um, this would not, for example, this would not parse. This is another class of error. Parse error on input. So like it literally just can't read your code because it's not sure how to deal with this like sort of we won't get into why exactly um, but ultimately it's ultimately because we have these two functions beside each other. If we had, for example, this would be valid, um, but this just doesn't mean anything. So there's no real way to parse that, right, and turn that into some real code. Um, whereas this is valid syntax because yes, this for all we know, if let's say this is like some mystery function, right? I have this like um, I make my own function. This is valid. I could make this. I could go and write this code. And it takes this equalities. At a high level, I don't know if this is, like Kyle said, if this actually is supposed to take a function like this. It's fully valid for Haskell to do that. Um, and so it's important that we have a good type checker, which tells us information about our code and where we've messed up. And so this is where we messed up. And so ultimately, like, I'll say, like, this is again, it's very simple here. We can kind of see what we've done wrong. It's still we can still take the simplest viewpoint of it, um, as we should be able to, and see that I was expecting a string, but we gave it something else. Um, there's only one right answer here, and we've given two wrong answers in a row. Um, but ultimately, like, as soon as I see this guy in any of these functions, I kind of immediately assume that I've done something wrong, or like that I've not fully applied a function. And I just go look for where that is.
Yeah, I would say just as like a heads up for those who are maybe new to the language and don't understand why he says that, because I think like it's a good red flag, but like a more definite way that I look at is, and I guess we haven't. This is fair because we haven't talked about type kinds, but like to me, if the kind of the type is different, then it's not partially applied, right? And so like string arrow bool
Yeah.
has one arrow in it, whereas char has no arrows. So that's like if you want to like you can literally just count the arrows. That's probably an easy way to start. Be like, okay, expected has 3 arrows, but actual has 2. So that means that I've applied it one too far, or it's expecting a function with 3 arguments. I'm only giving it one with 2,
Yeah.
right? Um, so that yeah, I think that's how I do it. Is I just look at the arrows. But
Yep.
if you see an arrow in one of these type mismatches, yeah, good red flag to be like, okay, it's probably something on it partially applied.
Yeah. Yeah. I'm ultimately just trying to keep it as simple as possible here.
Yeah,
Because we haven't talked about kinds necessarily yet.
yeah, but just count the arrows without
Yes.
getting into kinds. Count the arrows.
Yes. Exactly. Which is ultimately
What
what it
kinds
means.
is,
And
but
yes.
yeah.
Um. Anyways, so um. Well, actually not quite technically, but it sounds correct. Like it's the same idea. Anyways. Um. Yeah. So like just count the count the arrows. Um. And you will see that there's a mismatch of arrows, and that means that you have not fully applied something. But yeah, so there's only one real logical answer here. Only so many ways to check if something is a palindrome. We could even get more advanced in our logic. We could get into like more performant code to check our palindromes. Um, in case we have a palindrome HTTP service, where
Yeah. I
you can
mean,
ask us
if
if
you have to if you have to check if like a million lines are a palindrome or something like that, you
yes,
can optimize that simply by just checking if the first and the last one are equal, and then recursing again.
yeah,
Because you're going to get to the answer quicker by going from the outside in, as opposed to just reversing the whole thing and then doing inequality.
yeah. So there's
But
there's there's ways
there's
we
ways
can
to improve it.
yeah
Yeah.
there's ways we can optimize, which we can look at, but we don't really care about them at the moment. We're just kind of stating that there's a million other ways we could write this expression, um, and they will all have the same core shell of, like, this takes a string to a bool, and then this takes a string as input, and is named as palindrome, or whatever we want to call it. Um, yeah. So next aspect is, and I guess this was just part of our code from messing around last time, but uh, this is a this is a constant that we've defined, um, and how we would do it. And you'll notice that the similarities are very striking, in that an expression, sorry, a constant value in Haskell is very much just like it looks like a function, because like everything in Haskell is just a first class value. So like, what does that mean? And I'll go back to what we were talking about with syntax. There, like, you might at this point think this is syntax, right? This is syntax. You would probably assume, um, and yeah, these three things. Let's say the only thing that is actually, or sorry, and this equals here. The only two things, so four. The only two things that are actually syntax are this and this. This is just a function, and we checked it out before, right? We looked at the type of equals, and we can ask the type of it because it is a function. We can't say type of equals, for instance. This is going to fail. Um, and yeah, so ultimately, like, we are creating a functional. Sorry, this here is kind of creating a functional value. And there's one more key way we can write this function to make that a little bit more apparent, which we can say that palindrome is equal to the string. Sorry, is equal to the lambda, right? So you might be familiar with lambdas in other languages. All they are is just simply like the core bones of a function. And
You might also know them as anonymous functions or
yes,
arrow functions. That's what they're called in JavaScript or whatever.
right. And they are the core logic, right? They are the core logic of um, what a function is actually doing. All a function is doing is and how it compares to what we think of as a constant in Haskell, um, is that it's an I kind of think of it as like a more generic constant. Um, so, for example, we know that value is always going to be equal to true, right? We're going to have no arguments about what the the value of of value is. Um, but also too, like, we're never going to have a argument here about what the output of bool is. We're also never going to have an argument about what the input to palindrome is. And even too, like, if we tried to do this in a different way, it would never make sense to say int. We can't check the as a int a palindrome. I mean, you could get really really technical, and you could say, well, what about the digits 1 2 3 4 3 2 1? That's a palindrome, and like, okay, sure, but this is a string. Like, this is a string. This is a integer, and they do very different things. Um, there's also no real challenge in Haskell um, to turn this into a string, right? But ultimately, we can only do the logic of checking if something is a palindrome if the input is a string. And so, right, we've established two things about our function and how they relate to a value. Um, and okay, just do that. We have established that the input is always going to be a string. Even if there was more things that I could say that this takes in, um, I have said it's a string. So the type that it's checking for is a string, and we know that this type is always going to be this string, and we know that it's always going to return a bool. And I've declared that it's always going to take a bool. Um, Now we have an expression or a way of taking in that input and returning a boolean. And so we can see that we've done that through this logic of checking if it's equal to the reverse of the string, right? Um, so how does a function, like, we haven't really talked yet about how a function like factors into this here. All the function is doing is allowing us to overload from some constant, right? So we could say this here, um, and actually this here would be a we'll call this val2. This would be a another constant that we defined here. This would be a bool as well, right? So this takes, and this makes sense that it's a constant, um, because it doesn't take any input, right? It's always going to have the word constant, and it's going to check if the reverse of constant is equal to constant. And so we can look at this and we can say that val2 is always going to be equal to I'm going to say val2 is always going to be equal to false. And here again we have yet another constant, which is going to be also a bool, right? So you know like this is kind of somewhere in between of what we have, right? We have something which we would call like a true constant, right? It's a true constant. There's no arguing about that. We have this what is really a constant, but as we can see, that constant is evaluated by an expression, and then we have a function, and a function just allows us to pass different arguments, right? Different input in certain places, right? In key places. Like this just creates like a almost like a position where we are going to put string in. And so yeah, that's ultimately all we've done there. And this looks less familiar, but it's ultimately the same thing as this. It's not ultimately, it is the exact same thing. You could even argue that this is a bit of a syntactic sugar, how we had it before. And the compiler will, take that away at the base level and turn it into something looking like this. So now, like, why I went through all of that as well is to understand a bit about Haskell expressions, because we have this we have this idea of lambda calculus, and we're not going to get into it too much, because ultimately you probably have already done some lambda calculus without even knowing it, is what I'll say. And all that lambda calculus really teaches us is that there's a system we can use that we can ensure that all of our code remains coherent. So like there's not two meanings to our code, or there's not two different ways that something could evaluate. We want to make sure that if we look at our code, right? If we look at this, for example, we want to know that it's like how it's going to evaluate. We ultimately want to be able to read it properly, and so I can know the syntax and I can say how this is going to evaluate. I can also use similar to bedmass, like how we had bedmass in math. Like if we have 1 times 3 plus 4 times 5, we can know that 4 times 5 is going to evaluate first. Sorry. 1 times 3 is going to evaluate first, and that's going to be 3. And then 4 times 5 is going to evaluate and give us 20. And then we're going to, after we've done our first order of operations of 4 times 5, or doing our multiplication first, we can then do addition, right? According to our rules of bedmass, we can see that brackets comes first, exponents, then division and multiplication, and then lastly addition and subtraction. And so that's why we're going to perform the multiplication first, and then our addition, giving us a final answer of 23. Um, and so we we've learned bedmass so that we can all look at this. Maybe you've seen the really stupid um, stuff on Instagram where it's like everyone's arguing about how this evaluates, and you'll have like, there's only one right answer here, and we already know it's 23, but you'll have someone come along and say that, oh no, you're supposed to do this first, right? You're supposed to do this first, or something. Actually, I'm gonna get rid of the brackets because that would actually change things. Um, but we can all know, we can all objectively state that anyone who says you do 3 plus 4 first is wrong. They are objectively wrong because that is not how the order of operations work. And so we want a similar idea in Haskell. And here we have this idea. I've done here. I've added brackets to say this should evaluate first, right? And I can kind of put these brackets in arbitrary places. I could say this, for example. I could say this, but then this is not going to type check. And that, why would it type check here? Let's just show this. It's again saying I don't know what you're doing because we see our lambda here. There's an unapplied function, and that's because reverse itself is a function. So this doesn't make sense. But here, what I've actually done is I've said that this should evaluate first, right? Ignore everything else. Evaluate the inside of the brackets first, and then give that result, right? Whatever that returns, give that back into this expression of string is equal to something. And so yeah, we just want that pure disambiguity, or the pure lack of ambiguity, or lack of clarity on how things are going to evaluate. And so now the key thing that I wanted to get to here is just how like a function, like why this syntax matters, and why this syntax actually makes reading functions so much easier. Let's say, for example, we want to have a function which takes a list of, we're going to say a list of integers, and it's, what does it do? It just returns them back. It's going to add 1 to each of them, right? So f is a function which takes some x's, and it's going to return them all incremented by 1. And so we are all probably familiar with the map function. So a map, the type of map is a function which takes a function, right? It takes a function and it applies that function on the list and returns a resulting list back with the transformed input. And we can actually see this at our type level. I have chosen here to keep the type the same, but map actually doesn't require that. I could return a string if I so desired. I just don't. I just don't here. So I'm going to keep it as an int, and this is going to mean that I am going to take an int to an int and return. I'm going to give map a function which the function itself takes an int and returns an int. I'm going to apply that to a list of ints and return an int. Or sorry, return a list of ints. It's harder to say the types than it is to read them. Um, as my defense. But you're probably all familiar with this functionality in other languages. You just are not familiar maybe with the type signature. But you'll come to learn that this is really nice that we have this type signature, which like definitively tells us what we are doing. Um, it makes it so much easier to read than if I come into some function and I see like x's dot map um, f. That's all the information I have, and someone else wrote this, right? Like Kyle wrote this code. I've never seen this.
Beautiful code. Don't say anything about it.
Luna thinks so too. Uh, and
Yeah, she
yeah,
was coming at you for saying that.
yeah. So, which,
That's
yeah, I mean, it is important to remember with all learning that um, we have to kind of check our egos at the door, as going with Kyle's joke, because this is like, you know what, Kyle might be looking at this and say, I wrote this perfectly. This is so beautiful. This is like look how small this is. Like I have less code, and that's what I've been taught to do. I've been taught to have less code, um, which like is a good thing. It is truly a good thing to have less code to solve a problem. But I don't know what X's is. I don't know what F is. All I might know from knowing JavaScript, um, or another language, is that map is a function which um, you know works on a data structure. I don't even know it's a list actually. I don't have that guarantee, and I have a function which transforms that contained thing. And I actually I might not even know that, but I'm gonna guess at that. Whereas in Haskell, like I definitively know this is what is being done. Um, and most of the time, if I gave you, for example, is palindrome, and I told you it takes a string and returns a boolean, you can probably intuitively understand exactly what I mean. And that's just really important, right? We're not going to be working on our code in isolation. Um, and so Haskell teaches us sort of good coding practices for how we can make self-documenting code, so to speak. And I say self-documenting because you should still communicate what your code is doing, um, to the best of your abilities, and as concisely and you know verbosely as you can, to make someone else's life easier. But even just this tells us ultimately everything we need to know about what this function does. Right? Like I could cut this entirely out. I could completely hide this from myself, and I would know what it does. I would be able to tell you immediately what the expression or what that function body looks like. And further, um, mentors of mine has said that you should never need to look at a function's body to know what it does. Right? If so, I'm gonna keep using Kyle as an example here. And sorry, Kyle, I'm about to criticize the heck out of fictional you, but if Kyle wrote a function here that um I just couldn't I needed to come in and understand the expression, to understand what it's doing, then like he probably wrote like a really funky looking code, like really funky looking piece of code. And like for example, if we look at like what we have as options, I could fully say that this is just the function f, um, and I guess I need to say that's a string to a bool. I don't really have that option, but this is a little bit harder to see what it is we're doing, right? if I look at this, I have no idea what exactly is happening. I don't actually technically need to put the type signature in. It would tell me what the type is without it would infer, right? It would infer what the type is, and that's because the compiler is very intelligent and it can reason from the ground up that if this is a string and then this is a function which takes a string and returns a string, and then this is a function which takes two things, right? It can reason all the way up from your input in terms of this must be a string input to this must be a bool in response. But again, we want to document our code as best we can, so I am going to put the type signature in. It's also going to help me in the long run to put in my type signatures. I promise you that. Um, but but yeah, the key thing is, and I'm jumping around a little bit here, but we just don't want to write code like this. Like even though it's cute that we have this very quick name that we don't need to type out, that long. Um, okay, it's definitely easier to type out. It's a lot worse for anyone else who has to come and read it. And so the same problem applies to our exodus.map, and that's why we got into that discussion. So anyways, I'm going to comment that out. And how do we actually use map in Haskell here? And we were going to use this to add one to our function. So okay, I'm gonna create an anonymous function here. This is going to take in our integer. I'm going to call it my int, just for fun. I like that better. My int, and then we're going to say my int plus 1. And we're going to do that on x's. Right, so we can write a function like this. And this is a valid function. We can see that we can probably all understand intuitively what this is doing. Right, we have a list of integers. Right, we have a list from 1 to 10, and then this is going to give us back a list from 2 to 11. So yeah, so now um, where do we start with this? We were talking about why this sort of syntax matters. And so you can see that I'm using an anonymous function here again, or a lambda. We're going to call it a lambda from now on. But I actually can write this in a couple different ways. I could instead, so I'm going to say f prime. I know I'm breaking my name signature here, or my name rule here, but bear with me. We can also do this, and this is the same thing. Because this is and why can we do that? That's not super intuitive for why we can do that. Let's look at a little bit more of an intuitive example of why that's valid and why that will type check. A more intuitive example would be this. And you might say, what the heck do these two things have to do with each other? And that's because they both follow the same rule. They both follow the same rule in that all is palindrome is a reference. So if I said to you, we have this function x, or sorry, we have this value, this constant value x, and it's equal to 3, and I said to you, I don't know, let's say x plus 1, then, and I asked you, what's the next step here? With it's you might be jumping ahead a bit because this is so simple. It's not plus one. It's not to add, because we don't know how to add x to some phantom value, right? We need to know the value of x in order to do addition. Fair enough. So how would we do this? We would say we would just replace, right, in place, like we would replace x to be 3 just in place. That's the key word here. Same with is palindrome. Is palindrome is just a reference to a lambda. And so I could then go and say that this is, I'll put some placeholder here to show that this is just a place where we put our code. And then that placeholder gets replaced by our lambda. So, this is now, right? This is a valid step we have taken, in that we've just replaced the name with what it actually refers to, which is a lambda, right? Which is and ultimately lambdas are kind of the most important thing in programming. You might think objects are really cool. Objects don't really do anything until we apply some function to them, right? Like an object or data, right? I kind of think of objects and data as being one and the same most of the time. The only difference with between an object and pure data is that they have the ability to have functions themselves. But I ultimately nothing happens until you apply a function, right? We can we could have a program here which defines like a million constants, like y is equal to 4, z is equal to 5. And we keep doing that. Like nothing is going to happen until that's at least of interest to us humans until we apply a function. And so we're just going to do that here, and we're going to apply our function. And so how does this now evaluate? This is going to evaluate by saying, how we apply this recipe. And a lambda ultimately just tells us where to place our inputs, right? So we have this kind of placeholder name, which we can see matches up with the variables in the expression. And it's going to result in ABBA is equal to the reverse of ABBA. And we're just going to then go and check that out. We're going to see, is ABBA equal to the reverse of ABBA? We do the math, we do the logic. We see that ABBA in reverse is ABBA, and then we check, if ABBA is equal to ABBA, which is true. And so that's why that syntax matters, is that like, well, ultimately the syntax gives us a lot of freedom for how we define our expressions, but it gives us a lot of freedom in a way that is very clear how it works. There's only one way it can evaluate, which is not the case in other languages. And it's also very clear how it evaluates. But yeah, so I think we've done a lot there. And I believe that suffices for the basics of expressions and how functions work in Haskell. I guess sorry. There's one. Here's where the value comes in, is that we can then let's make this a little bit more clear. Let's call plus one a function which takes an x and does x plus 1. I can now say plus 1 easily here. And right, this takes an int, and it returns an int. I can now easily call map plus 1 on x's, and it's clear to me how it evaluates. Because plus 1 is just going to simply be replaced by the actual expression itself. And then we can apply that expression to our list. Yeah. So I won't. Yeah. There's not really a good way to show why that's so awesome yet. We will find why that is awesome very soon. And yeah. So I think this was all just us messing around here. This is another example that we've gone through in a past lesson, so I won't spend too much time on it. But we can see we can get a little bit more advanced with our expressions. And I guess I did lie. There is other syntax in Haskell. Um, Again, we have gone through 90% of it. Um, and we've gone through everything that you would absolutely need to use. You don't need to use guards, but they are helpful. And this is an example of guards. So this is kind of like an overloaded case expression. So instead of, our simplest case is our classic if then else, um, case expression, where we can see if my expression is equal to true, then do A, else do B if false. And we want to make that a little bit more generic because we want to have an ability to pattern match on a little bit more. And so we could also write this in a different way. We could have a case expression, or let me just do this instead. We could say case x of true, do this. Case x of false, do this. And that's the same thing, right? Do A, do B, do be do. But now we want to get even more generic than that, and we want to have like multiple things that we can check. So here, if you're familiar with FizzBuzz, when we're going to count from 0 to 100, whenever is a multiple of 3, we are going to, whenever it's a multiple of 3, we are going to print out fizz. Whenever it is a multiple of 5, we're going to print out buzz. And whenever it's a multiple of both, we're going to print out fizzbuzz. And so what this gets into is like overlapping cases, right? So this, like, and what I mean by that is if I was to put this last here, this would never get hit, right? This would never happen because without even looking at our expression that encodes our logic, if we think about our logic that like only in the case of it being a multiple of 3 and 5 will it print fizzbuzz. That's like kind of a like if that's true, right? If both of them are true, then well then both of them are true. If it's both a multiple of 3 and 5, then this case here is true. And so this would never reach, right? This would be unreachable code here because we would never get to it. And so that's why we put it first here. And we're going to check, does this expression here evaluate to true? Right? Is the remainder, for this n that we have, is the remainder when divided by 3 equal to 0? And also, is the remainder when divided by 5 equal to 0? If so, give back fizzbuzz. Um, and yeah, and then similarly here, if it's only equal to, or sorry, if it's only true that the remainder when divided by 3 is equal to 0, then print fizz. If it's only true that the remainder when divided by 5 is equal to 0, print buzz. Or sorry, not, I don't mean to say print buzz because we actually don't do that here. We just give back the value. Um, and I'm remembering a funny thing too, which is like something that surprised me with like case expressions in other languages. If I didn't say, for example, return here, it would then go to the next case and like continue evaluating. Like it wouldn't stop checking if the cases are as such, or if the cases are true. Um, but we don't need to do that here, and we don't need to do that here in general in Haskell, not just because of like case expressions and how they work or whatever. But you may have noticed that like even in is palindrome, uh, you know, we're working like a lambda, right? A lambda doesn't need, and no matter what language we're using, we don't need to say, return, right? We don't need to say return of this logic here, because we just know that we're going to get back the value um, that results. So similarly here, our result is just the literal string fizzbuzz. Um, and similarly, fizz and other all that. Oh yeah, and then otherwise, I guess um, we show n. So we show, for example, here if we said show one, it's going to turn our integer um, into a string. Similarly, if we were to say show true, it would turn true into a string. And that's just this is an overloaded function using type classes, which we'll get to eventually, that ultimately allows us to define a way to take a type and turn it into a string. Um, and so we can see how we do that for integers and for bools. Um, yeah. And so now, um, you know, like what we've written here is all we've written here is really how to get back a string. Um, the key thing is, and I can tell this from our type signature, that we have not actually done anything. Um, like we haven't done anything interesting here. Like um, I'm gonna assign this to a variable just to like kind of because I'm in a REPL. So ignore the aspect here. But if I was to say, fizzle, um, and dyno save. Let me just remove this. Oh yeah, because I have no implicit prelude. That would normally not happen. I'm just gonna get rid of this for now. What the heck? Um, okay. Well, I don't know why that's being annoying, but there we go. Um, yeah. So this hasn't actually. What I'm trying to show you is that there's nothing even I kind of lied earlier when I said that functions um, are doing something useful. Um, because they're not necessarily, or they're doing something useful for sure, but that doesn't necessarily mean that they do anything at all. Um, we only know that we're doing something at all when we get to something like FizzBuzz, where we're going to actually show something to ourselves, right? So, like, if I say print one, oh, I think if I do that, that would, yeah, there we go. Print one, that's actually finally doing something, right? Whereas if I just say x is equal to one, I haven't really done anything, at least that the user cares about. And in this case, we're the user. We want to see back what FizzBus 100 gives us. So actually, I can just call this here. And I can see that it's evaluated and gave us back something that we care about, which is prints, or yeah, something to look at here. Um, and it's only when we call FizzBuzz that we actually apply Fizzle, right? Um, and yeah, and what I'm ultimately trying to get at, I don't think I'm liaising into it very well, is that there's this idea of laziness in Haskell. So let's say, for example, that we had a function here. Um, we had a function here. Um, modify. So modify is a function which takes this. We're going to get to take the exact type of our function above, um, and it's also going to take an int, and it's going to return a string. Um, and all I'm really trying to show here is laziness in Haskell. Um, so um, if I have f here, I have my x. Um, if x is, or sorry, let me do it like this actually, just to kind of showcase laziness. So we would apply f to x normally, right? So we would say our result is equal to f x, um, and yeah, so right, that is true. We can write this without this actually evaluating, right? If let's say this is like some massive function um, that we have written in JavaScript. This is going to, as soon as we get to this expression, or sorry, as soon as we get to this line, it's going to check and evaluate what result is. Whereas in Haskell, we just kind of keep this as a recipe, right? We just keep that if we ever need to check the value of result, um, we know how to find it, and we're going to apply that expression. Um, so, but that's not the case here. Or sorry, that is the case here. We just keep it. We don't evaluate it, and we say, oh, sorry, I need my let in. Let result equals f of x, and um, if x um, remainder 2 is equal to 0, so if it's even, then give back nah, else result. Right, so we can do something like this, and it's not even going to check, right? It's never going to check if um, if it's you know if it's it's never going to run. Sorry, it's never going to run fizzle on um, on on the input. And I can actually prove this. So I can see that result is a string. And so I can say, I can do string concatenation, right? So we have our plus plus, which takes two strings and adds them together. And I can say show on an infinite list. And this is going to compile. Uh, oh, um, oh my gosh. Also from Prelude. There we go. Fizz Buzz 100. Oh, sorry. I'm silly. Um, this is going to compile, or sorry, this is going to evaluate.
Do you wanna show fizzbuzz one dot, or you wanna show fizzle one dot dot, right?
Yeah, I was going to show this never actually evaluating. Um,
Oh, okay, sorry, maybe I'm behind.
um, well, okay. Let's actually. Here, maybe I'm getting too fancy here. I'm going to say result two is equal to um, show of an infinite list. Right. So yeah. So that did not fail, right? That's not still running. Not trying to like evaluate what does an infinite list mean. I could even do something further here. I could say this to get really fancy with it. Kind of retrying my attempt there, and I'm gonna say show of result two. Or sorry, not result two. It's already been turned into a string, and I'm just gonna say um, take 0 from this infinite list, and that will be my result. Um, this comes from the take module. That should work now. There we go. Fizzbuzz 100. Same thing. I like in JavaScript or another language, this would not actually ever work because this would try and evaluate. It would first look at what is result two. Whereas Haskell is very neat in that it does the minimum amount of work that you need to do in order to get the answer. And so, like, if we just think about this, like, there shouldn't really be a need to look at, the whole list of result two. Um, we are only taking 0. So if we take 0, then we know that, you know, we like, we know that we're always going to get back nothing. And so why would we ever, you know, um, why would we ever evaluate the list first in that case? Um, yeah. So that's FizzBuzz done in a million different ways. Um, this is getting a little bit more advanced, and I said to leave this as a homework question. Applying our knowledge of our code, and I'm going to keep it that way. Because I think it's actually a very good one, and it will be hard to talk through. Um, we have a simple min max. I think we maybe I'll leave these ones in here as well. I encourage you to go through them. This is from last time. Again, I also encourage you to go through this. It's just doing things in a bit more polymorphic a way. Um, and we actually have already kind of done that, so I'll get rid of that. Um, and yeah, Um, where do I actually want to get to? Oh yeah, okay. So let's get into like a real world example here. So you're going to be working with APIs. That is a absolute guarantee. Um, and some APIs kind of suck. Um, you know, I saw a question on Reddit Learn Programming thread. What is an API? And my hyper philosophical self couldn't be couldn't be straight away from my temptation to say that everything is an API. Um, we think of like when people talk about APIs, they talk about how they're probably referring to an HTTP API, and that like we're going to make a request to ChatGPT for it to evaluate some prompt. And we think of that as being an API, right? One that we're hitting over a network. Um, but if, an API stands for an application programmable interface, which if we think about what that means, um, it's ultimately also talking about functions. So again, I'm very much in opinion land of my
No,
own.
you're right. If I can clarify it,
Yeah,
it's really
please.
just um, like API is just an interface for other developers to use your code.
Yeah,
Just the most common, like an SDK is technically an API. We just call it an SDK because it's more specific.
yeah,
Um, an SDK also is kind of like more a toolkit, whereas an API is like you're actually interacting with an external system.
yeah,
So there is actually a bit of a difference, but you can kind of think about them along the same way. They're grouped in the same way. Um, but yeah, API is just anytime you're actually interacting with someone else's system, those interactions need to be handled through an interface. So it's basically just a protocol agreement of how the two are gonna interact,
yeah,
and that's all it is. So it could be over HTTP, it could be TCP, it can be like it could be a file that's SFTP'd over to you. I don't suggest that, but like
yeah. Some sort of networking.
some kind of just like agreement between two parties is
Yes,
really what an API is.
and that's why I think it's good to think of our functions as APIs, because
Yeah,
we are like when we write code. If I write a function like unwords, or like which just takes a list of words and concatenates them all together, um, currently undefined, but I'm using this somewhere else probably, right? I'm creating this function to use it somewhere else, and similarly, like someone else might also be using this code, um, that is sharing a code base with myself. Um, so like if we think of them as APIs, it kind of helps us to think about how we should document them, which is very well, so that other people can come in and use them no problem. Um, right? We want to make our functions as reusable as possible, where applicable. Um, and so we have a we I guess we have a system here called My Learning Space. We're going to use as the fictional API here. And My Learning Space is also a great example because I hate My Learning Space. Um, it sucks. Um, and, you know, what we're trying to model here, and this is obviously just data I've made up, is that this is data coming from the API, and we don't really have any guarantees about it, right? We have a string. we have a string which is supposed to represent the person's name and their numerical grade out of 100. It's supposed to be, right? We don't have that. Um, or sorry, that's what it's supposed to be. Um, but you know, if you do enough coding in, um, you know, less strong type systems, you'll see that sometimes people will for example, give back a -1 to signal error or something went wrong here. Um, they'll further overload it to say, uh, you know, -1 is supposed to mean that no authentication, right? And this is somewhere in the documentation. -2 means invalid user type or whatever, and then we have this kind of like this sort of like fake enum of what these represent, and that's because like the only types that some of these languages have at their disposal are kind of our basic types like int, string, Boolean, um, and etc. and so forth. Maybe a tuple, maybe a list, a record, but like very very weak enums in some cases. And so, like, it's very possible that from this API, we're going to get back invalid data. And so maybe this -4 actually means something, or maybe it's a mistake. It could also be a mistake. This is definitely a mistake. This is not a mistake, but they have awful code, and they accidentally returned the database query, which is also a string, right? This is valid. This technically is valid code here, um, yeah, and I've actually seen this before, where like there was a research database that I went into, and the title of it was literally a database query. They messed up in their
Did
code.
just didn't execute it.
Yeah, yeah, like it was.
Yeah, I've
I
seen that
I
too.
I think what happened was it didn't find the value that it was looking for, and so I think it failed in some way, and so that failure I think led to some fallback case, which like erroneously for some reason was give back the database query. I don't know how you get there, but that's my guess. Um, yeah, and and so like as you can see, I've kind of modeled. There's a number of errors that can happen here, and we don't really know what our input is always going to look like, but we need to model a system that is going to work effectively, right, with this API. And what are we doing here? We're just trying to turn. We're doing something very simple, which is I believe, and we'll see this later. I forget what the code looks like. Um, we are just trying to give them back a letter grade, right? So if they're above 80, so Alice, for example, would get back an A. She should get back an A. They should get back an F. They should get back a B. They should get back an A, a D, A. Um, I mean, they would get back an F, whoever that was supposed to be. Um, I don't know. I don't know what the answer is here. This really depends. And I don't know is the other answer. There's not really a valid thing I can say. I can't say this is an A. I'm tempted to say this is an A, but I'm not actually sure if that's an A. I'm not actually sure if this is an F because like did they just do some math wrong and maybe it was supposed to be a 3 or and they I don't know. But the key thing is I can establish that while I can't establish what grade it should be, I can simply say, I don't know, man. I have no idea. And that's actually perfectly fine. Um, oh yeah, I guess I just left them as function stubs, eh? Is that what I did? Okay, perfect. So the first thing we're going to do is we're just going to convert this into a map, right? A map data structure. Like a map is very like we ultimately have a map here, and that we um, you know it looks like a map. It's a key value pairs, so it's a map. Um, and we can do this by simply saying, let's say grades, student grades, and we can say map dot from list student grades. Cool. Um, and that will give us back a map. That's all we need to do. So we have this map function. Let me go here. I'm going to use the normal Hugel. Um, function from list. And we can see that it does that exactly. So as long as we have a way to, what this says is, as long as we have a way to order our keys, we can take a list and we can turn it into a map. And so we have a way to determine order of strings, so we can do that. Um, cool. Now, the next piece is we want to define our logic about um, letter grades. So we have integers here, right? That we're going to take as input. Case grade num. There's actually I'm going to use. It's best for me to use a guard here, so that I can kind of like be a little bit more dynamic with my logic. So I'm going to say if grade num is and I'm gonna again let's for anyone who's like catching on here, the function name is naive, so hear me out. Um, grade num is less than 50. Give back f. Um, grade num is less than um, less than my brain's not working here. Less than 60. It is a D. Um, grade num is less than um, sorry, grade num is less than 70. I don't know why this is taking me forever. Grade num is less than 80. It's a B. Um, and otherwise, it's so 80 and above, right, is going to be an A. Um, but does anyone see any issues with this code? Especially if we look back at our input here. Um, yeah, does anyone see any issues with this?
It doesn't catch Rick's 201.
Yeah.
So you're just going to return 201 as an A, which
Yeah.
should be an error of some sort or something flagged.
Exactly. And similarly, it's not gonna catch Morty at -4. It's gonna say Morty is an F because and which is just the logic that we've said, right? Our logic sounded great. I don't think we disagree that like we've done something reasonable here so far, but it's not complete, right? There's a like we need to continue with our logic. We need to continue building on our function to make sure that it's robust. And so we have two more cases that we kind of need to add in here. And you can say if grade num is less than 0, then I guess it would be an error. And we could do this. We could technically say error here, but this will crash our program. So we don't want to do that. We don't need to crash our program because the API failed. Um, but we can't continue like this. So I'm going to copy this over. Um, and we have to move to this type signature here. Why do we have to move to this type signature here? Because this allows us to fail, right? This allows us. This maybe type says this is the maybe type here. Maybe A. I'm gonna use this here. We either have just our data, or we have nothing, right? So we have this data type of maybe, which allows us to kind of encode failure. It can also be used for like optional cases. Like if we want to have an optional argument, we could use maybe. Is another case. But here we're going to use it to model failure. And so instead of returning a grade, right? This is the key difference: is that we add in this maybe context, right? We've added in our first bit of context that wraps our grade. So we don't have just a grade. We have like kind of a modified, um, you know, data type, modified version of a grade. Right? We can't just. We'll get into this more, but now we can't be naive with this. I can't then return the result of this and operate on it as if it's a grade. And let's say Python, for example, Python, for example, you would just simply say that this is a grade. You get back a grade, and that's all there is to it. But then you would change this to say grade num less than 0 is none. Right? It's just kind of like this, like hiding in the background definition of none. And this is going to cause problems because now you're going to try and say, let's say you want to bump a student up or whatever, right? They deserve a better grade than they got. They got like a B, but they actually put in a lot of work, and they should get an A. You really think you should override the system, let's say, and you try to increment your grade, right? And we take in our B, and we get back an A. Right? This is all we need to do to increment our grade, is that if we are given a B, we get back an A. Right, and this is just a function which takes a grade and returns a grade. Now, if we were to try and, like in Python, say increment grade on the result of a sign letter grade, right, for -4, this is going to fail at runtime. Right, this part is going to succeed because it's just going to return none, and it's possible to do that, right? It's even possible to write increment grade in a way that works, but the Python compiler or interpreter really is going to say this looks great because it doesn't know whether or not you're going to pass -4 in or whether you're going to pass in 50. So if I pass in 50, this is going to succeed at runtime. If user 2 comes along then, right, a second user comes along and gives me -4 as input, this is now going to crash at runtime. And I'm going to be very confused why sometimes my code fails. And now an expert Python dev would say, brother, you're an idiot. You just need to check if it's none, right? And you'll go through this logic of saying, if assign letter grade is not none, or in a more familiar syntax, let's just say not equal to none in Python, then increment grade. But like the key thing is that Haskell ultimately enforces that you handle this error properly, and it can tell based on the type system if you've handled this error properly. And the way that we handle this error properly is through none, right? And so it's through maybe. And like the other key thing is like if someone, let's even like you're working on code bases where a ton of people are using the same code, and someone for whatever reason, maybe their use case is a certain thing, they come along and they say this is unnecessary, because this is just x. We don't know that this is -4 or that it's going to be -4, but we just say this is unnecessary. This will never be none. I think it's never going to be none, and then we just say again assign letter grade naive x. Right, maybe we get that back and we do increment grade y. No one's ever gonna you. This is still going to compile, and this is still going to break. And so Haskell is nice in that way, in that if we were to change that, right, if we got rid of this check, it would ultimately be able to tell from the maybe data type that makes no sense. What you just did, you are like it will literally say this. It will give you a type error like couldn't match expected type maybe int with actual type of int, right? It will say these are not the same thing. You've told, like, you're trying to operate on this as if it's just an int, but we don't know for sure, right? The logic has encoded that this is not for sure an int, and we need to handle that. So let's actually go and do that, and we're going to again use maybe here, and we need to first say what was successful, right? So just simply tells us that this value is successful, right? And so this type checks because we both have the maybe aspect and we have the grade aspect, which lines up with our maybe grade. And so we know that all of those are well formed. Now, if I say grade num is less than 0, I have a valid way of returning, of communicating the results here. And I can just say that this is nothing. Further, I'm going to want to change this. I'm going to say grade num is less than, I guess it's possible to get 100, so I'm going to say 101. Just, or actually, let's just do this. Equal to, less than or equal to 100. It is going to be just an A. Now, our otherwise means something different in that it's going to be greater than 100. So now this is a failure. So it's kind of neat. Also, too, I'm noticing like how as we continue to scale up, we handle our ranges properly, right? Like there's if we think of it as a big circle, right? Like we have our big circle of what is an integer, and within that circle of what is an integer, we have a subsection which is valid, right? We have a whole subsection which is valid, um, and we can create a proper grade for. But we have this whole other sort of section of not possible, impossible grades, and this validly encodes between the two sets, right? We go from the integer set to the maybe grade set in a proper fashion. Um, and we can further later we can reduce from this. Um, but we won't do that quite just yet. We're going to look at um, another data structure, and we're going to ask the question: how do we? So we have our we made our map earlier, right? Of students and their grades, and we want to give them their proper grades. So okay, cool. I naively again I'm going to do something here, which is I am going to um uh I guess I have my map in. I'll call it mappy. And I'm going to fmap assign letter grade. And this looks great to me. Um, so fmap. Well, okay. So yeah, fmap. I might be doing too much in one statement here, but fmap is a function that allows us to work with this structure. Um, and I'm going to come back to this in a second. I'm going to start with the simplest part first, which is that this is not actually valid. And we'll see why this fails. Oh, sorry. That's not valid. Oh, yeah, and I created maybe here. Maybe is already in Prelude. I'm just going to do that. Oh, why is this? Pardon me 1 second here. This is just I'm having something weird happen with Prelude. Um, Let me just do this actually. What am I? This should just import everything. Um, I'm just gonna hide what I've already done. Right. 333. Okay, perfect. So I wanted to show this error here. Um, of course, this might be um, a little excessive how much I'm getting into the type errors here, but ultimately, even though we're starting to get into more complex functions where we're mapping over data structures, right? We're dealing with a map data structure. We're starting to create a context to our data. Um, we can see that the type errors still work beautifully well, and this exactly tells me what the issue is. It's saying that I have said somehow with my code, right? This code says that the sign letter grade is a type which returns a grade. Sorry, it's a function which returns a grade, but it actually returns a maybe grade. And so it tells me you want to do this. Let me just get rid of that. Perfect. And so I have a map of strings where each is the name and a maybe grade. I'm going to introduce another piece of Haskell here just to make our lives make our code a bit more readable. And it's just the simplest thing ever. It's a type synonym. And so a type synonym is just another name for something. So I want to call this a name instead of a string, right? And so this is just at runtime or at compile time, I'm going to replace this with a string. But for my own code, I want to call this a name. And I can do this with the type keyword, which, as we can see, is very straightforward. And so I guess did we already? Oh yeah, we already recompiled. I already have name somewhere. I must have already defined it. But yeah, that should work. And okay, that works correctly. And now we have a question here. We want to check a student's grade, right? We want to check if they exist, if they're in the list of students, and if they got a valid grade or not. And so there's a couple of things that we have to work through in order to. I'm not really sure about my type signature here, but there's a couple of things we need to work through in order to check that we have a valid answer we can give a student. For one, does their name exist in the list? Is it a valid name? And is it a valid number? And so let's start with this. I don't know why I have a string here, I'll be so honest, but we have a map dot map of a name, and let's say we're just starting out with like with the we haven't applied this give students grades yet. We're gonna instead do this as part of this function, and so we want to return a maybe grade. And so I'm going to guess that it's going to be a maybe grade because just based on everything we've worked with here. And I know Haskell pretty well at this point, I guess. But yeah, I'm gonna guess that it's going to be a maybe grade. So the first thing I want to do is I want to check if they're in the list. And so how can I do that? I have this function lookup, wherever it is. Let me see. If I click on S, and if I go to a Haskell package and I click on S, it'll bring up a search menu that I can look up a function for. And I can see that it is a function which takes a key, a map, and gives me back a maybe A. Cool. So like I'm not the what's cool here is that I'm not the only person using a maybe A. It's a very commonly used data type, and so that's what I do. I'm going to say case map dot lookup. I guess I need the name to look up as an argument. I'm now realizing. And I need the name. I'm going to pass the name in here. Case map. Okay, look up the name in the map. And we will either get back nothing. And I'm not sure what I'm going to do there just yet. Or we're going to get just, the numerical grade. Okay. So now, we kind of need to check two things as well. Maybe arguably, we should check this first. We should check if their name is even valid. So let me just. I'm gonna just cheat this for a second here. Is valid name. And is valid name is just going to. We're gonna say that we actually properly implemented this, and all it's gonna do is just give us back, just the name. And we're gonna. We're gonna implement that logic in a second. So case is valid name of nothing. I'm not sure what I'm going to do there just yet. But case valid name of it is in fact a valid name. Let's call it valid name. And then we're going to do one more case statement, which is case. What did we call it? We said assign letter grade. Of our numerical grade that we got back from the map. Case this assigned letter grade, numerical grade is nothing. Then I'm just gonna say that we're not sure what we do there. But in the case of it actually being a numerical grade, we'll have gotten back a letter grade, and well, I guess in this case we would just get back our letter grade. And this is almost complete. So we have figured out that we have figured out our happy path in that we have a valid letter grade, for a student with a valid name that exists in the map. In this case, all we would do is just simply return nothing. Cool. Any questions so far about this? If you don't understand this, it's important that you do before we move on to the next part. So please feel free to ask questions. I'm also just going to do this. Cool. Okay, it doesn't sound like I'm hearing any questions, so just checking I'm still on the. Okay, good. So we are working with structures here, right? We're not just working with int and grade. We're also working with structure that gives meaning to the data that we have, right? And that's important because in other languages maybe we could get away without using the structure, but the structure gives us necessary context, right? If I had just an int, I don't know that that's necessarily like a grade, but I know that if I see this, that it's a list. It's a you know it's a set of students' grades. It's a bit more information that gives meaning to the underlying data. Um, yeah, we have a lot of structure in programming, um, and it can be it's both useful and also very cumbersome to work with. So like I think this is a really cool example, and I'm going to throw it out as like a very clear example of something I thought was really cool. Um, is we use maps. The library we use for WebSockets on our backend uses maps to optimize queries. If you're familiar with Cassandra DB, I actually learned that they also recently also learned that they do this as well. Is that they use they use maps to aggregate user queries. So um, ultimately, what that looks like is we have a map with some user and some data they are interested in, right? Um, let's just call it a promise for some data they're interested in. That's not a literal thing. I'm just kind of making this up as I go. And we want to give that user back, some data they are interested in. Right. That's ultimately what we're doing here. Um, in any context, we're definitely going to do this. We're definitely going to promise the user some data back. Right? They're going to make a request to our API, and we're going to give them that data that they asked for, assuming that they have access to it. And so if we have a number of users that are interested in data, we can model that as a map of queries or things they are interested in. And we can use this map to encode like who is interested in what. So maybe, user A is looking for the string hello. And user B is looking for the string hey. We can model that, and we can say that we have this map, right, which just kind of looks like this. User A is looking for hello, and then the other user is looking for hey. And so it's not clear why this matters in this example, but having this map of users and what they are interested in allows for massive optimizations in terms of your database queries. But it's important that you still keep things separate. And so, like, maps are this data structure which, in this context, allow us to do some really advanced modeling, and allow us to keep track of some context, right? As soon as we were to get rid of this map of user, we actually have lost important information that accompanies our core data, right? The core queries are accompanied by some context. And this is a very common pattern that you'll see in programming, is that you have a context and you have a data type. And that context wraps a data type. This map being one example of that. What you'll notice as you get more advanced in Haskell is that Haskell allows us to take advantage of this pattern very, 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 very well in a way that is simply impossible in other languages. It is like we trust me, Kyle and I have tried and are trying to model this sort of thing, or model the things that Haskell can do for us in other languages, but it is literally impossible. Um,
Yeah. C sharp,
yeah.
we're doing right now. There's limitations that just make it impossible.
Mm,
Good news is that some languages are uh, like stealing from functional programming, and they are bringing these things into their compilers, but it's a slow process.
Yep. And you can do you can do pretty close to it. But like
Yeah, you get a
you
lot of the same benefits. You just have to be aware of where the drawbacks are.
right, and you have to kind of know like you have to kind of make a pseudo system. It feels like I feel like the C sharp
Hmm.
library that we're using is like it does a lot of work for us.
Yeah, yeah, yeah.
But in Haskell this is easy. Um, and the reason for this is actually just directly in the data types. So we have this maybe a, for example, which is maybe is our context, right? And it has there's some definition of maybe and how maybe works. But maybe is a context that is generic. It can work with any data type. And like that makes sense. That absolutely makes sense that it should be able to work with any data type. There's nothing restrictive about that should be restrictive about encoding whether or not something should be optional. And so like what's the simple example of that is we might have we could just for fun we could make a function that takes a maybe a and it takes that a and turns it to or sorry takes a maybe a as well as a function that that operates on the contained value and gives us back a maybe b. Right, so we can do that easily, and we can encode this um, and kind of like ignore the context, and we don't have there's not a clear way to do this in object oriented. Um, and I'm not going to get into why that is. But there is just simply not a clear way to do this, and that we can write this in a generic, overloaded sense. Um, we need to know more about the relationship between maybe and the a in order to run a function like this. And it becomes specific to that context or specific to that particular block of code. And we can't generalize it. In Haskell, however, we easily can. Further, we can do something even crazier, which is we can kind of say we don't care about either. This M is some context. This M is some context that we don't need to know about. Like we're not even doing anything with the context. So like why should we really need to know about what it is? And we can say, right, we can't directly write this function here. We need classes at this point, but we can write. There's a way to create this logic in Haskell, which is really ultimately this is the most generic aspect of what we are trying to do. Yeah. I mean, I guess the more generic would be if we had, let's say, we changed the M, which we could also do. We could also make it like, MM as our, I'm going to call it M2 actually. Um, we could change that for sure. But there's a lot of times, like, it goes back directly to our example of like, what are we more interested in? Are we more interested in, I'm going to call this G. Are we more interested in how to write F, or are we more interested in how to write G? Are we more interested in how to maintain a structure and apply some operation to the contained data, or are we more interested in how to return data in general? Um, what's more useful to us? And I guess the answer is a little bit too overloaded, in that like there's probably a case where this makes sense, right? Like I don't know. Honestly, this has become so generic that I'm not even sure where this like applies. This is just kind of like this is almost like any other function to me at this point. But this the F is really important because it says keep the structure as is. Don't destroy the structure. And so we actually did this. We have fmap here, and um, fmap is a function which sorry, fmap is a function which applies a function onto a value contained in some context. So that's exactly what we've done. And we can how have we done this? So the way that we've done this is through a type class called functor. And we're familiar with type classes already. We have a very simple type class, which is the show type class. So show is a function from that type class of show, which takes that value we are creating an instance for and turns it into a string. So for example, I can ask I can ask my compiler if this is going to work, and if this works, then I can show true. Then I can tell that there's an instance defined for true. And if there's not an instance defined for that data type, like let's say I just make a new data type, data x equals x, and I say show x, it's going to give me a compiler error, not a runtime error, but a compiler error that we haven't defined a way to derive, or sorry, a way to show x. And I can actually easily do this by just saying deriving show. And that should actually work for almost everything. If I wanted to create the instance in a custom way, I could do that, but I won't get into that today, just for time's sake. But yeah, so this is the same thing in that this is a function. Sorry, this is a why does it keep doing that? This is a type class which operates on a context, right? So for one example of this is maybe. You can see it's defined for a number of things. A function maybe. And we can see that it just applies a function on maybe. How does it do that? Sorry. Is it first if it checks if it's nothing, and then doesn't apply anything. But if it's just an A, right? If we're if such the context that it's just wrapping an A, then we can apply that F onto our A and get back a result. So Haskell is very intelligent at handling context and allowing us to generalize in that way. So I can actually do this a little bit simpler. I can use something called do syntax, and I can Well, I'm not even gonna actually. I won't start with do syntax. What I'll start with is another function that'll clean this up. Um, and okay. Oh, oh, okay, fair enough. Crap. Um, well, okay. I'm gonna pretend that this type checked because I don't want to get into the more um. Here, let me just do this. Actually, I can do this. Um, okay, I'm not gonna.
Does it get bound through when you do grade like that? Does it get bound through to the next? Because you're doing two binds here. Right?
Yeah, no, I know why it's not.
Okay.
I was trying to show. Okay, let's just pretend this type checks just to keep things simple. Because I'm gonna immediately go on to do. Um,
Hmm.
and which will make my life a little bit easier too. I don't really write
But
it like
I think
this.
it even kind of proves your point that like it can be complex to think about it in this way, and do is makes it a lot easier to think about it.
Yeah,
Right?
totally. Because I'm ultimately so what this is saying is pass the result of this into this, and then pass the result of this into this. And so like it's kind of our first example, or one of our first examples of like Haskell expressions being very free form, and that we have a lot of like yeah, we have a lot of freedom in how we can write them, assuming they type check. Um, they didn't type check because I'm technically saying um, give the result of this. Not technically. I'm literally saying give the result of this to this, whereas I want the result of this to be passed into assigned letter grade. So I can make
You
my
can
life
map his valid name
yes.
over that map and then find. That's
Whatever,
probably
whatever. It doesn't matter.
what. Yeah.
Let's not get into that. But like,
Yeah.
so ultimately, I can make my life a little bit easier here. This is the same thing. Um, this what we're here using is a thing called monads, which ultimately and people like to think of them in very complex ways, but they're not really that. Um, oh, I mean to look for this one. They only really allow us to ignore context. Um, and so this might look a little confusing, but ultimately all we're doing is passing our results forward, right? We just have to create a type signature here that allows us to do that, and that's why it looks kind of funky. But all we're doing is passing our result forward. I can do an equivalent thing with do syntax where I say something like this. Right, so you can see that here it was getting its argument from here, so it looks like it's not getting applied, but it is. And then we can also get the letter grade by saying assign letter grade. And ultimately, before, what this was looking like was assign letter grade to valid name, which makes no sense because assign letter grade takes an integer. So what I actually wanted to pass here was grade. And so now I can just say return letter grade. And return is also a part of monads, in that all it says is just return, like wrap this value in the context. And so this is now valid code. Once I get rid of this. And I can say now, look up valid grade. Galen in my from list. Galen, he got a 0. No instance for show grade. Oh, that's true. We're just going to derive the show instance for that. And so I got a 0. If I gave myself a -1, I would get back nothing. If I got back 101, I would get nothing. If I got back, if I got an 88, I would get an A. And so, you can see as I continue to pass values into it, there's not really a way to break this code. And that we have written like very robust code. On top of that, we've also used some Haskell power to create something that is very easy to follow, right? So I can see that this gives me back a grade, this gives me back a valid name, and this gives me back a letter grade. And I can apply, or I can pass these values back into particular pieces of the code. You might also be wondering, so if we go back to our original case here, what happens? What happens with is valid name when it's like nothing? Or what happens if we don't find the name? Yeah, I think we can maybe guess at what happens with the signed letter grade potentially, but even there, what happens in these cases of nothing, and what if, and maybe what's even intuitive possibly is that if the last thing fails, we get back our fail case of nothing. But does this logic run if we don't have a valid name? And does it run, or does it run if we can't find the name in the map? And the answer is in the context. And so this is now why we have a monad. And so the monad encodes what this logic should be. So if I look for this instance, where is monad of maybe? There we are. I'm just going to copy it in here, just so we can play with it a bit better. a monad of maybe um, encodes what should happen if it fails. So um, what this says is that if map.lookup is nothing, then this entire thing will return nothing, right? So if I, like for example, if I look up Galen, I'm going to get nothing, even though I have a valid grade, right? 88 is a valid grade, but I just looked up Galen, who doesn't exist in the map. Um, and what happened was that failed at that step. So yeah, so now and that actually might not be super clear, and we will look at another, like we'll swap out this maybe in a second, but ultimately, if any of these fail, then none of these are going to run. And where does that come from? It simply comes from the behavior defined in the monad. And so whoever created the maybe monad said that I want this context to be able to short circuit, right? This, if I chain together a bunch of maybe statements and the first one is invalid, or the first one is a nothing, then there's no point in checking the next 100 checks. There's no point in running any future code. And so we actually, how does that look? And that's why it's important to know sort of it's important to know about this because, okay. Sorry, it's important to know how this looks because this is itself just a function. Um, and this function, what is it taking? This function is taking its left side and everything to its right side. And so we can see it has its left side, right? Its left side, and it has its right side. So what happens if this is nothing, right? So if we have nothing is equal to dot 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 dot, then this is going to pattern match as being this case, right? We're actually not even going to look at this. This is a syntax to say we're not even going to look at what what is on the right side. We could name this like right hand side, and it would do the same thing. But we could even just say we don't even want to create a name for it because we don't need to. We're not ever going to refer to it, and yeah. So what this right hand side could encode, and it's clear if we look at it in this way, this could encode a number of chains of maybe statements, right? This could encode, or this could contain on the right hand side a huge chain of maybe statements. And again, that's all we're doing here, right? This is very similar to just like chaining in functions in general, but it's a very particular type of chaining. And one that allows us to deal with the context and also use the context to throw effects. So this is why, like, a lot of people like think of Haskell monads, I mean, as being effect systems. That this models failure. And so, that would be why they say that, is because we can use the instance of the monad to determine how this works and how to combine our logic together. And so that's a freedom that we don't have in other languages. We're kind of stuck in this imperative land and it's not a very even strong imperative land. Um, yeah, we definitely can't even go as far as to do this um, in normal programming. Um, any questions there? That was a lot. Okay, I'm gonna make this a little bit more clear now. So how I'm going to do this is I am going to use either instead, and I'm going to say that this is is so what is the either data type? Either either gives us back an error, or our data that we are interested in. Right? We have left error. In the case of the left error, or the right x, um, is at the value level. So, for example, if we change, I'm going to need to remove this just so that it's not going to conflict with anything. Let's say we change isValidName to either a string or a name. I guess this was just changed to right. Right is similar to just in that it just contains the data that we are interested in, and gives students grades. This would be. I'm gonna change this so that it's an either string or grade, and then assigned letter grade is going to give us back instead either a string or a grade. And this has a little bit more information to it, and that we can say was less than 0, was greater than 100. Um, does this type check? Probably not. Not yet. Oh, oh yeah. And I'm gonna make my own lookup function. And it's going to take a map of name int, and it's going to return to me a either string or int. And how I'm going to do that is I'm just going to like kind of coerce this, so to speak. Oh, I want a name here as well. My map, or sorry, name and mappy, and we're just going to say map.lookup case map.lookup name and mappy of just the name, so we found it. I'm going to return this as a write, so I'm just going to change the type that we return. And then if this is nothing, I want to give back a more informative error. So I want to say, so looking like when I'm writing this code, I kind of know a lot of context that I don't know when I might be using this code or using a function which uses this code. Um, but I know here what I care about. So before, right, when we were running our code, we would see that we got back nothing, and we didn't know why. Um, it could have been that we didn't find the name in the map, or it could have been that the grade was not valid. But here we know the reason is that name was not found. And where is valid name? Oh yeah, okay, we already got that. So now this should work. Oh, except for the fact that I'm saying I'm still using my old lookup function, and I'm gonna change it to use my new lookup function. And I'm just going to change these all to being right. And now, if I run my code again, I'm going to see back name not found. What's interesting too is that I haven't changed my code here much. The only thing I actually changed about my lookup valid grade function was that I used this function instead. And I changed the context that I'm working out of. So, yeah, I'm no longer using maybe, right? And it's important we understand how we got from here to here. But we have ultimately just switched out maybe for either string. And now it works ultimately the exact same. We don't need to rethink about, or our context hasn't forced us to rewrite our code from scratch. Because we just understand that it is a context that works in some fashion, and we can work with it. And we see that that succeeded. If this is 101, was greater than 100, nice. If we have this as -1, we have it's less than 0. So even like just here, we have this kind of bulletproof code that works with context and shows us kind of the power of Haskell. We are way over time, so I'm going to stop myself there. But yeah, any questions? Thanks for sticking around.
No questions for me. But yeah, I was playing. I've never really used map myself. I've always just kind of hacked around with even just sometimes. Sometimes I know I should be using map here, but I'm using a list of tuples or something. But there are. I think I was having a little play with that as you were going along as well. Yeah, it's probably something I should use a bit more directly.
Yeah, maps are going to be more efficient than a list of tuples.
Oh, is it?
Yeah.
That's good as well.
Yeah.
Because you don't have to, like, a list is just a linked list, right? So you have to go through, like, you're still going to be going through each individual item, whereas maps are more of like they use a hashing kind of index usually. So it's a little like you'll actually like hash by like a string, and then it'll know how to point to where that string is.
Yeah. So it's been optimized for those things that you often do, like looking up something. Yeah,
maps
sense.
are optimized for lookups because they use hash like a hash table kind of pattern.
Yeah.
Cool. Yeah, that's something I'll probably take advantage of. Yeah, I think there's even something what I'm doing now with the Twitter thing. I could probably I've got a list of tuples. I'm looking right at a list of tuples right now. So I probably should change that to a map.
Experimenting with the map, like for what you're doing, you probably won't notice a performance benefit or anything like that. But definitely, it can
Best
be one of those
practices.
things that, like for more complex and larger data sets, that kind of thing, you'll start to see performance degradation with large lists.
Yeah. Also, I'll say too that like I totally understand where you're coming from with like just having like a list of tuples like everywhere because I feel like when you get into other languages, this kind of like demonstrates another great point about Haskell, is that like when you get into other languages, it can kind of almost be like cumbersome to like remember all these different ways to interface with the type. Um, Whereas like you could use fmap on the list of tuples, and then you could also use fmap on a map. Like it doesn't it allows us to like overload um, certain functions to work regardless of the context. And then of course too, like map also gives us like other powers, like better lookups ultimately. So yeah.
Yeah. Yeah, no, that's definitely. I'll probably just do a bit of tidying up with what I've got already. So I'll try and weave the maps in where I can, just as much just as good practice, isn't it? Really. But yeah, cool.
Yeah, they're pretty useful, I'll say. Um, and like um, I feel like yeah, for project 4, which is like using WebSockets, like you'll probably want to have some um, good familiarity with maps.
Yeah,
Kind of
yeah,
unavoidable at that point.
makes sense. Yeah.
Did we collect names for who was all here?
I can off of memory, but
Okay. All right. Well,
I mean it'll be in the video, but
uh, I don't know because like
oh, because you don't
yeah,
you did at some point. I do remember you doing it, but
I have no
that's gonna be hard to find that frame within 3 hours of footage.
yeah.
I can try to think. If we forget anyone, then whatever they should have stayed.
Well, we are over
Yeah.
time.
I know, I'm just joking.
Yeah. Um. I actually like Nick. I'm curious. I think you understand monads, or right or um.
Monads. Yeah.
Yeah. I'm assuming so with how far you've gotten. Um. What do you think of that explanation of monads? Like it's yet another monad tutorial, I suppose, but
It's I know. I think that's really good. I think it's it's one of those things where monads, like, they seem so complex, and then finally it will just suddenly click, and you're like, oh, wait a minute, it's just another data structure that follows a certain pattern. It's
yeah.
like, you know what I mean? It's like it's functor, applicative, all those things, and every explanation does something similar. They go for these patterns, and but somehow for some reason monad just seems so much more complex. But really, yeah, it's just if you want to apply functions that result in the same monad as something's already wrapped in that monad, then you combine them and you get the results of it. You know what I mean? It's
Right.
But yeah, but yeah, I think also just showing that the bind syntax is just the do syntax is just sugar for the bind is it's a really good way of getting people, because I think most people will just use. I mean, I use do syntax all the time, and I quite like using some of the more Haskell kind of inline stuff where I can, but I think most people are going to get a lot of use out of do. So if they can see that that's just that, once they get comfortable with it, it won't take much digging for them to understand the bind syntax as well, I think. So,
Yeah.
No, it's good. Yeah.
Makes sense. Makes sense. Um, yeah, because that's like that's my biggest thing is like just like there's I feel like I don't know like there's so many infinite ways to like explain monad in like a complex way, but it's like it's like the whole point of it's to simplify, you know.
Yeah. Yeah, I think it's the more I think about it, the way I think about it is just we like to put little wrappers or tags around types for like the reason that you've been talking about. We want to then be able to operate on things inside of that. Well, that's kind of functor.
Mm-hmm.
sometimes we end up with functions inside of a map because we've been doing some stuff. Maybe you partially applied it, so that's when you need applicative. And sometimes you end up with things inside of a container, a function that takes a non-containerized thing and returns a containerized thing, and I want the result of that. The problem is it's simple when even you can see it, but trying to get a nice explanation that cleanly says it that people can grok is well, no one's it's something that everyone's doing, as you say, and yes, another video. I think it's just a familiarity thing.
Yeah.
But once you realize what it is and that it's no real different to a functor, well, I mean, it's different obviously in form, but in really complexity and things, it's just another similar thing to a functor or applicative.
Yeah.
And it's just another pattern.
Yeah.
I think one of the other, as I've seen, is like, when I'm not sure. I remember is when, like, if you show, like, oh, if I get a monad, so let's say, well, I get something wrapped in a thing, and I've also got a function that's going to return that thing. You show that, oh, well, at first I've got to unwrap it, and then apply this thing to it, then I'll get it out. If you show them every time you're doing that, sometimes you can go, hang on, there's the same pattern appearing in all these different things.
Right.
And then you can say, maybe it would be really nice if I could just abstract that pattern out. That's what bind is.
Right.
And then we just call that bind. And then, you can kind of show that. But sometimes that can then be a lot of code for someone to look at and get, go from the pattern to from the thing to the pattern. But that's another way to do it. But I think your way was really good as well. I think it kind of gave that kind of intuition of it, like you can see it happening, if you know what I mean. So
Yeah.
Yeah.
That's another good way of looking at it, though.
Expanding, that's the way that I kind of understood it too, is when you see all those case statements expand and you're like, and that, like, because that looks like, your typical if else, like those your if else trees that you get into in imperative. Sometimes those get quite unwielding, and then just to see you be able to take that and just squish it into a couple function calls with this little operator in between, right? It's like yeah, it's crazy. I think that's one of the big things that sold me on Haskell, at least.
Yeah.
Yeah.
It's like every time you want to write you write a kind of fairly simple recursive type thing to iterate through a list or whatever type of thing you're iterating through. It's just, well, that's just a fold.
Yeah.
And again, it's just that's a common pattern. You're writing the same thing over and over and over again. Well, that could just be abstracted into a fold, and that works for anything that has a certain structure, if that makes sense.
Right.
I'll tell you, in imperative languages, I don't even write for loops anymore. I just fold with a lambda.
Yeah.
It's like, and it's like, okay, cool, whatever. Just, I don't like writing for loops anymore. It just feels weird because you have to deal with the index or you can do for each, right? But still.
Of course, and it's obviously it's possible to write good code in imperative languages. It's just Haskell stops you you have to handle these things because you then abstract these things into these structure things. These things therefore have to work over a structure in a certain way. It forces you to write your code in a certain way for it to fit the patterns and the structures, and stops you realize you've done something somewhere in a code base of thousands of lines of code and to figure out where that mistake is going to come back into it.
Yep.
But I think there's just something really nice about Haskell.
Yeah. It's funny too how, like, I think I'm still learning this myself. How, like, the fact, like, when you hear that it's like static type, it's so interesting to me. Like all the different things I've heard about, like, dynamically typed languages are amazing. But like I think the first thing I thought with like static typing is that, like, oh, I have to do more code, and it's like actually it's not. That's not true at all. Like it's like
it can be. It can be. Let's not we need to give Hindley and Milner good credit where due. Because type inference is the reason why we're not writing a ton of boilerplate in Haskell, right?
Yeah, but like I mean, even just like the amount of, like, okay, like there's like all the handling of cases,
Sure.
like
Yeah.
a
Yeah. Yeah.
static
Yeah.
type.
Like monads do a lot, but I'm just saying, like, let's give credit where due, because that's the biggest thing. Because even in for example, even in C#, right? We have monads. We it's kind of hacky, but we have a monad. But we still, in oftentimes, are like we have to specify the types like all over the place.
Right.
So it does make it clunky, and it's a lot to write, right? The reason why people like dynamic languages is that because they can say var I equals 0, right? They can just do that.
Yeah.
They don't have to care about like what it is. They should, but they don't have to.
Right.
And so Haskell's kind of like brings that in too. It's like when you're writing your code, you don't have to write that all the time, but it'll tell you. So it's kind of like in a more advanced, like an advancement on top of that,
Yeah.
right?
No, you're right. You're right. I think
I think people are just not aware enough of Haskell, to be honest. They just think it's like a research language.
Well,
It is
I
easier.
literally hear people that I've literally spoken to someone. I did a Scala training course at my work, and literally the guy was showing me Scala. I spoke to him a bit about Haskell. And he goes, "Yeah, I've never understood it because how can you do anything with a language when you can't? You've got no side effects." I was like, "No, Haskell does have side effects. You just have to wrap it in the IO monad, and you have to, appropriate. It just means you have to tag it and know that you are doing something that has side effects." It was like there is that kind of like assertion people will make. It's like, oh, how can you do anything in a language with no side effects? You're like, that's not
What do
even
you
what
mean no
it is.
side effects? That's the whole point of IO.
yeah.
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 It's
Yeah.
just there's some real misnomers about what Haskell is out there.
Sure.
It's weird.
Yeah. I wish like Haskell had more like I feel like everyone who gets into Haskell becomes obsessed with it, like so obsessed with it that like I'm thinking of like okay, Traversing Media is like a guy I followed for like learning Python, and he's just like he doesn't have a passion for Python or whatever. It's just like if we're gonna use Python to do this. There's not really there's not much like that in Haskell and it's like okay, we're gonna you're more likely to see how can we abstract over the category of Hask in a composable, reflective manner. And it's like, okay, I have no idea what the hell that means. Like, I mean, probably because I made it up, but like half of it sounds made up. Like there's a guy I follow on Twitter, just for fun almost, named Iceland Jack, who like all he does is like abstract category theory, and like he'll just be like, oh, like I don't even know how to communicate what the heck he's talking about, but he'll just like give no context to like these mathematical proofs that he's like putting out there, and it's like, what does that mean? Like I want to understand it, but I don't, and like to be honest, you don't need to understand it either. Like you could get away with without ever understanding how you can use Haskell for mathematical proofs or something else. I don't know,
But that's the thing often with like maths and is that a lot of it comes down to a certain kind of just ability to read their syntax and the kind of just know what the terminology means, and it can be hard to. And this is a bit like Haskell in terms of that, whereas like it can be a bit hard to wrap your head around those ideas, but then it allows you to convey those ideas so much more tersely as opposed to writing out each of the steps. And I don't know. I think it is one of those things where I think I don't want to be one of those people who says like I understand like a lot of people say like you want to keep the kind of mathematical names for things because it's kind of the history of Haskell.
yeah,
But I do almost think it's kind of like it'd be almost good if you could kind of come up with a toy version of Haskell where you just do not mention any of the mathematical words and just call them a wrapper or a container or a tag and call it a pattern.
yeah,
And do you know what I mean? And just use really kind of normal words and things for it. And I reckon people would take to that quite nicely and just go, oh, you're just doing that and that. Okay, fair enough.
yeah.
And then you could just go, okay, here's Haskell. There's a bit more to it, but it's effectively the same thing. You just got to know that this word means this word means that, this word means this. And I think you'd probably see a bit good, bit more of an uptake, I think. But yeah.
I 100% agree. Yeah, like I don't know why it's never been called like a tag or just like, you know, because that's ultimately what it is. It's just like a tag that tells you information about the type. Like even too like like I find it really interesting how people talk about monads. Like they'll say like, oh, this is a monad, and it's like, no, like a monad is like a type class. Like, which maybe I'm being like the one who's sounding, like esoteric or whatever, but like like it almost does a disservice to call like a maybe, like call the maybe data type like an example of a monad, uh, or like, you know what I mean? Like it's like you don't need to understand monad to understand like the maybe tag, you know?
No, no, it's the thing of like it's better to think of like I said that these are tags, these are functions, and the bind function, which maybe again maybe not the best name for something. I think in other languages it's called something like flatten or flat map or something like that.
Huh.
Might convey to people a little bit more of what's going on, as it's just taking things with these tags and functions that result in these tags, and it gives you this kind of result. Um, it gives you probably a better user understanding of how to use these things. It hides probably some of the kind of the actual pattern that you're really doing, which is probably why I think some Haskellers don't like it as much. But you're completely right. It's maybe the reason why it's the maybe monad is because you've proven that you can use bind on maybe,
Right, right,
and that's what makes it a monad. Because you've proven that you can use bind on it, basically.
right. And like you know what I mean? Like it almost like overcomplicates like what a monad is. Like it's literally just like a pattern. Like it's just
Yeah,
simply a pattern, you know, and it's even like honestly like I feel like it's almost more important to understand like what is not a monad, or like what doesn't make sense as a monad. Like for example, if you had like a server config, it wouldn't make sense to make that data type a monad, because like sure you could technically do it, but like you're never going to use that interface. Why would you ever use the bind function on a to like in the context of a server config? That just doesn't even make sense, you know?
yeah,
Like you might use the IO monad to return a server config, um, but you're not going to make the server config itself a monad. That just doesn't make sense. Like, um, I don't know.
no, yeah, no. I get what you mean. It's again, it's just it's often this way when you take things and turn it into a formal kind of language around things. It's useful in terms of making sure your I's and T's are crossed, T's are crossed and I's are dotted. But when you're just trying to get that kind of understanding of what's actually going on, it can obfuscate just some kind of the plain thing, which is it's a monad because I'm going to use bind on it more than once.
Yeah.
So I therefore it was worth me going away and abstracting away that pattern and saying how I want bind to work on it.
Right.
If I'm only ever going to do basically a bind once ever, it would be worth to go and do that. I might just handle it in the code right here and there, even though that was effectively a monadic bind. And it's like, well, yeah, but it just wasn't worth me going to do the other work.
Right.
If that makes sense.
I
Um, yeah, no, go ahead. Yeah.
Yeah, no, I think I love that too, because like um how I would like to explain a type class is just like and all a type class really is just simply like you're saying exactly. I'm going to use this many times, so let me just
Yeah.
like overload it, you know?
Let's just write that down somewhere so I don't have to keep writing the same. It's just abstracting away the boilerplate. If I'm going to write the same thing every time I use this thing, well, it's like writing a function that does this, does those things. You're just going to want to make sure that you can always use just bind on it. And if you're going to make functions that things, you put them into type classes so that you don't have to keep handling the same kind of logical things each time.
Right.
But yeah, it's like you said, it's supposed to be a convenience. It's supposed to make it easier, but sometimes, yeah, it's getting people to see that convenience is the hardest bit, I think.
Totally. Totally. Yeah. Um, but by the way, on a completely different note, like, I'm curious. Have you ever like looked into like effect systems? Like this is kind of like complete opposite end. Like, um, but like I feel like the one area of Haskell that I'm like, well, and I don't understand it yet, but like effect systems um are something I want to look into, I guess. So I'm just curious if you've like used them before, or, like
No, the first use of it really is in Obelisk with the reflex kind of things. I suppose sometimes the people talk about um, even things as like monad transformers as effective as an effect system
yes,
in its own right. So there's a kind of a slightly more generalized idea of effect systems that I'm not hugely aware, knowledgeable on. But I think we've getting my head around. I think it's definitely getting there. But once I've really got a good intuition or good kind of like I know how I like to think about. There's like reading the theory. There's like learning how I like to think about it and how I like feel like it works for myself.
yeah,
And then I try to marry those two worlds. Once I've kind of married those two, I haven't quite got to the point where I think I've married those two worlds with the kind of the yeah for the kind of events and things like that. But once I've done that, I think I'll probably be in a space where I'd probably have the mental headspace or enough knowledge to look at effect systems. Because yeah, at the moment it's just something I go, okay, I do what it tells me.
yeah,
I don't really understand it.
yeah,
But I've got a feeling it's to do with closures because of carrying the time. You're kind of carrying that state within inside of something, but
yeah,
I wouldn't know. I don't know off the top of my head. Yeah.
yeah. It's I mean, yeah, it's very similar to like a state T in a way. It's like Kyle, I feel like you have a good explanation of like that, but like
So I say it again.
like no worries, no worries. Like how to think of like events and like I was saying, and I feel like you have a better way of saying this. Like it's almost like a state T. Like I kind of think of like an event as like it's kind of just carrying some information with it. Um, like
Yeah, yeah.
events
I
are
don't know. I
weird.
kind of think of events on their own just because like I'm so used to using um, like imperative languages with events, where events are like literally in some languages events are like syntax.
Yeah,
Uh,
true.
so it's yeah, but you could model it as like a change in state, right?
Yeah, yeah,
You
it
could
kind of
model it as
is.
a change in state from event not triggered to event triggered.
Yeah, and I guess it like keeps track of like the time or like the
Yeah.
ordering of events and all that. So, um, yeah, I don't know. It's almost like it's like a more, it's like it, I feel like it's like closest to a state T, but it's almost like if you had multiple diverging state T's that somehow kept track of each other.
Well, yeah, and I think maybe that's also one of the things that I think there was an issue with State T. Is I was watching a video of his name's gone for me, but it's the guy who did. What was the? It's gone from my completely gone from my head. It's do you know it's like before Servant, the big kind of web thing, wasn't it? Haskell
Yeah, so or
uh,
not Servant.
framework. No, it was the big one. Yesod web framework.
Mm.
Um, he was the guy, the main guy behind that. I saw him talking about State T, and this was just before I think this was just as STM came about, and they were talking about STM for concurrency. But he proved mathematically that State T will lose data if done through concurrent systems. I won't. Let me see if I can find that video for you and
Mm-hmm.
post it to you in case I'm just getting it
Interesting.
wrong.
Mm-hmm.
But there was that, and I think that's why then other effectful systems were started brought in.
Yeah.
Because if you start doing things with concurrency, you need to move away from state. Now he was just saying, well, just use STM, and you just put your state into an STM basically.
Mm-hmm.
But I think other effectful systems like Reflex came up for that reason, that it deals with concurrency better, I think. But let's see if I can find that video.
You know what I think too? Like,
that sounds interesting. Send that to me if you find it.
Yeah, we'll do.
I read, so like the effectful repo has like a little bit of a explanation on. I don't know, like, around concurrency. I haven't read anything around that. But like it was kind of interesting. This is like the motivation behind effect systems. Ultimately, is that you can model your code in a way that does lose state. That you don't really you did write that way, and maybe you did intend to, but it's confusing. Like for example, a state T wrapping an accept T is different from an accept T wrapping a state T, but they both have the same effects, right? But like one of them will keep track of the state and then fail, and then one of them will fail before keeping track of state. So like effect systems is like, we don't want that kind of like ambiguity, which is it's not really ambiguity, but it's like it's reading ambiguity. Like if you don't know the ordering of the monad transformer stack, then it's ambiguous. And so you can like lose state that way. Like if you had like put state and then fail, I believe it will fail depending on the ordering of the. It won't track that state depending on the ordering of the monad transformer stack. Oh, cool.
Yeah. So the video is literally called "Everything You Didn't Want to Know About Monad Transformer State." But like you're right, there's always ways of managing these things, isn't it? Like if you know what you're trying to do and what you're trying, you don't mind losing. If you architect it or design it in such a way that the only data you're losing is things you don't care about, then it doesn't matter.
Yeah. Well, you know what, and I feel like where I'm trying to the lesson today was very much motivated in that I want to find a way to ultimately describe Haskell like a toy language. I think like for beginners that's like absolutely important, and I think it's very doable. And I think like just getting into the idea that like this is just a wrapper, container, tag, whatever. Like kind of allows us to move towards the idea that like a programming language is just an interface between you and like binary code, and we have all of these layers to kind of make things more readable, more simple, more understandable once we come back at the top level. Like, and we can, of course, if we were to try and read binary code, we'd be like, I have no idea what this means. If we then go up a couple levels, we go to C, we can like read it. It's like a little bit more challenging. There's a lot of information there, and like there's bigger functions, which are like unavoidable. Like it's challenging. Maybe we go from C to Python, and it's like much simpler. We can probably read how our code works if we write good code. Whereas like Haskell, going from C to Haskell, we can do the same thing, but we can also keep building more complex functions and then simplify them. Like almost like folding in like the level of complexity that we have at a top level. Like so that like if we see we have like a complex boilerplate, we can just sort of say, oh, this is my function to apply to lists, and now I can just call this function, and I know that it does some complex operation, but I just know that, I can just continue to abstract up in a neat way that doesn't like break, I guess. You know what I mean?
Yeah, and I think there's no, definitely. I think that's I think it is the kind of next step to kind of really popularize Haskell. It's just that kind of coming to a kind of more toy-friendly way of language around it. Mm-hmm. I think it'll be interesting. Yeah, I mean, it'll be interesting to try and kind of tie it all together. But it's coming up with a nice clean set of examples where you can see it kind of building up. Like
Yeah.
if you want to do this, um, it's a bit like, have you ever seen, or was it NAND to Tetris? Where it's like you build a computer using NAND gates inside a virtual computer inside of using just NAND gates. It's kind of maybe going, instead of going from that point, maybe going from NASM upwards. Like this is how you would try and do something quite simple in assembly. And as soon as you try printing an integer in assembly, it's quite even that involves quite a lot of quite a bit of code.
Yeah.
And then you see that how that wraps up into something like C. Then you can show that, okay, that's fine. But I think what you want to find, if you can find, is you want to find the example that breaks it. I mean, assembly, what breaks it is just to do something simple takes this amount of typing and blah, blah. I think with C, you want to show the kind of unsafe or safe, kind of the issues that you will run into. C. What breaks C? Why would you want to build this? What does the abstraction buy you? Well, it would be good if, yes, we do have types, but it'd be good if I could define these types and make these types. You know what I mean?
Yeah.
So I think it's that kind of thing. But again, like you say, using language, which is thing is like one of the ways that number theory was explained to me, when it was like, if you think about it, at some point people understood the concept of there was nothing, and they understood the concept of there being the kind of natural numbers, i.e. you could count things like there's one of that, there's two of that, there's three of that. And then they kind of came with the ideas of you can subtract things from this. So if you had five of those things, you could take away three of them.
Yeah.
But negative numbers kind of came out of breaking that number system. You came up with negative numbers because someone said, well, what happens if I take away 7 from 5 things?
Right.
And they went, well, you just come out and the other side and you get your negative numbers. And you can kind of see this through a lot of things, that a new part of maths was proven by, well, if you extend that logic, you end up breaking it in some way. How do we handle when you break that? Okay, and that's a lot of number theory, or like mathematical theory, is kind of based on this idea that a lot of maths was kind of invented or discovered, whichever way you might prefer to think about it, by breaking a number system by following its own logic. So if you can think of examples like that, like you break assembly, or you break the usefulness of assembly because you're like, this is something. Okay, that's why C was invented on top of it. If you then take C and you go, well, the C is great now, it's solved this problem, but then this stuff happens. No, I've broken it. How can I, and then you can show that Haskell then introduces this, and then it stops being, people can see that like the monad and all these things are just things that have been introduced because they do something, as opposed to just, this is an abstract sense of concepts, and if you understand them, you'll eventually write safe code. You can say, C's got all these problems, these things keep happening. I wonder how we could solve that problem. Well, maybe if we did something along these lines, and then you can see how Haskell, and then people will more intuitively understand it because they know what problem it's solving. But these abstractions weren't just brought in there because, well, it might have been for some people that it's nicely mathematically pure, but for the main reason is because they solve a problem because of something breaking. Does that make sense?
It's interesting too, because I'm like, how, like, for like assembly for C, like completely understanding or whatever, and I was like, how does it apply to like Haskell? And my first guess is that like, or like the, the levels to Haskell, like, I feel like it's kind of like what we were talking about earlier with like that static typing, in that there is like technically a lot of code, but it's easy to take that set of static code and then like overload it, so that like, because the problem, the breaking point with static code is that there's just a lot of thinking. The person who released the C# library that Kyle and I use has like a neat way of like explaining functions, and that a function is just a set of like maps from input to output. And
Yeah.
it sounds crazy when you think of like numbers, where like there's infinite numbers and they like map to infinite other numbers, and
Domain and codomain. Yeah.
yeah, and but like the thing is, like, you don't need to remember that. Like, you just need to remember to do +1, or like you don't need to remember that 1 plus 1 is 2, and then 2 plus 1 is 3, and then 3 plus 1 is 4, you can just remember that, like, um, the relationship that is encoded in plus 1. Um, you know,
I think it's also, yeah, no, definitely. I think it's also interesting. Mate, always, the one thing I think of Haskell is the one thing it can't really do. It's one of the reasons I kind of started looking in a little bit into the type level programming, because if you think about it, the one thing it can't really do very well is say, because the types and the values are so separate. Is if you say it's an integer, well, an integer is not an infinite. In maths, integer is a infinite set of numbers, but in a computer, an integer is not an infinite set of numbers, and there are actually boundaries. There is a bound set of numbers, and actually, the one thing that Haskell is not very good at doing, and it's one little kind of wrinkle, if you like, in terms of that, is you don't know if it's going to wrap around and give you a different number, because you've gone over. If you add one more to whatever the top number is, you come back out the other end, or whatever, which way around you want to do it.
oh,
So
yeah,
there are these edges in Haskell, but I think once you know that, A, they're not particularly common edges, but B, if you know that, that's one little bit of complexity and you're going to need to put into your code. I was talking to someone else and I can't remember, and I was like, I can't remember what I was specifically talking. I said, you kind of got a choice. It's like Haskell, yeah, the types can get a lot more complicated than in other languages, but you're either going to deal with that complexity in your type system, or you've got to handle it in your code. Right. And if you handle it in your type system, it means all your code has to then fit the safety of what you've said in your types. So it kind of guarantees it. Whereas if you deal with all your complexity in your code, you have to be sure you've written the exact right code. There's barely, that's why debuggers are so important in other languages, because you don't know if you've caught all the edge cases.
right.
But if in Haskell, like I said, there's only one, like kind of that one that I really know of on top of my head, and probably Stack Overflow from a non-tail recursive recursion. But they're kind of the only ones that I can think of. Maybe there's more, but I don't. And so keeping those two things in my head is not a hard things to remember. It's like, and if they did go wrong, you'd be like, okay, yeah, I need to put a case in that. Whereas in every language, there are so many of those edge cases where you're like, if you don't catch that when this happens, if you don't catch that when this happens, you don't catch when this happens,
Right.
you're going to have weirdness in your program.
Right.
But yeah.
No, I love how that's said. That's really, like, the gears are turning in my head around. Like, this might become a full on lesson of, like, going from assembly to C to other languages, and just
We've been wanting to do it. It's just we don't know how much value, like, if people would like that, or I don't know.
I think
Maybe
it has tons of value.
maybe we'll pull it.
Right.
Yeah, if we do it right, it definitely adds a lot of value.
Yeah.
It's a good one for us to have. We could even make that into a YouTube value or video for like why functional programming is kind of the next frontier, and why it should even be used with AI, right? Because, like, there's this everyone's talking about right now where it's like, well, why would you be even looking at Haskell when, like, AI is going to be writing all your code, bro? Like, you don't even need to worry about that. And so then the question becomes, like, well, why wouldn't you want AIs to be using robust software?
Yeah.
Like, would you not want AIs to be using something that they can't make mistakes in runtime, as opposed to just, like, you just have this AI thing that's living for like 10, 15 years, and people are just, like, asking it to do things, and it's just growing like 17 arms and, like, random, like, morphisms.
Yeah.
And it stops working, right? One of the arms gets cut off because of whatever, and then it can't. So yeah, like, I don't know.
It just hallucinates.
I feel like there's going to be a lot of, and maybe I'm just underestimating the power of AI. Maybe AI can, like, perfectly generate all of the test cases that are necessary to make sure nothing will break. But we've got AIs using primarily Python and JavaScript right now, and TypeScript right now. So it's like, and people aren't asking the right prompts. They're not asking it to do it in, like, the safest way or to use like X and Y principles necessarily. They're just like vibe coding, right? So it's I think Haskell will even become valuable there. So
I think it's also
Having
too. So go ahead.
I was going to say, having used a bit of AI to kind of generate me examples of something I didn't really understand, knowing how it can get itself tied into knots with the type system of Haskell doesn't really make me feel that very safe in the fact that without a type system, that it's not making some crazy
right,
things happen.
exactly.
It's like if it's getting tied up when you just need to make sure you connect all the dots in a type system like Haskell.
That's a great
What are
point.
you doing out in the wild?
Yeah, don't actually. That's a great point. I'm going to use that
Yeah.
because you're absolutely right. If it can't even figure it out when it's got a perfect type system to explain how things get stitched together, how is it figuring it out without that? It's just throwing shit together. There's immutable state everywhere, and as that thing grows, it's just gonna, yeah, it's gonna be fun. I mean, it's gonna be interesting to see,
I
like, because there's gonna be companies that are gonna be like become so unstable.
Yeah. Honestly, I had to write a C program, and like I'm not the most comfortable with C, so like I used it to do that, and like it was helpful. More, it was better C developer than I am because I don't do a ton of C. Um, and it was like just giving like a billion global variables, and like everything was just like a bunch of functions that don't take any arguments and they rely on like a million global variables, and then the ordering isn't correct, and like it was doing something that like I eventually like it was a good start for sure. I think with just how little I knew about it, like I think that's like the biggest power of AI is for learning, um, but like it produced crap. Like it was like, oh my gosh, I need to go through and just like apply like Haskell programming thinking to this. Like, how can I make sure that this is like acting in a functional manner? How can I remove all global variables? How can I remove all like weird memory issues that are coming up? Like interactions of memory and functions were just completely off. Um, so yeah, it was awful. But where am I going with this? Oh yeah, I guess like I think too like I feel like Haskell and like the Haskell compiler and yeah Haskell, and like the Haskell compiler and like ChatGPT or like whatever AI are like a beautiful marriage. Like it's like I kind of think of it as like two co-founders. Like it's like you have like the one co-founder who's like all ideas, all you know, we should do this, we should go to Mars or whatever, and then you have another co-founder who's like, how do we do that? Like, that's the chat, that's the GHC, and then the GPT is like, I have amazing ideas, and then you just kind of like funnel them through, and you end up with like something that's creative, but also like works. So
I mean, ChatGPT is great. I think it's much better than not in every case, but it's much better than Stack Overflow. You get it; it is more tailored to exactly what you're looking for, and I would say it's probably as right as it is wrong as Stack Overflow ever was as well. So
Yeah.
I don't think it's much worse than trawling through Stack Overflow for me. So I think for me that's all it's done. It's really replaced Stack Overflow
Yeah,
for me.
same.
I don't we go there
and you're not
much
gonna
anymore.
get like abused by someone in the comments who's like, this is a stupid question.
Yeah,
Yeah.
exactly. Yeah. It's much nicer than some
Yeah,
contributors.
yeah.
Yeah.
I miss that though. Like not like I never posted anything on Stack Overflow. I just always read, but I don't know, just going in and seeing it, you're like, wow. I'm glad I'm not this person. First off, but
Oh
like,
man, I used to have to wait weeks to get a response.
yeah,
Oh yeah.
Do you remember those days? You'd make a post on Stack Overflow, you'd get a couple watchers, and you're like watching it every day, every morning. You refresh to see if someone replied. Fuck. Now you got GPT. So
yeah.
Yeah. It just it's sped up that whole process, hasn't it? Yeah.
Yeah.
Yeah, it's great.
It'd be a fun project to say like try to build one of those coding agents through GHC um and like ChatGPT or some shit. I honestly personally want to do that myself just for like fun. Like I don't think it would work super well, but like I feel like how most AI coding agents work is they just like, oh, there's a bug here, like retry, and it's like, but like it will give like some other crap back. Like whereas like Haskell errors are like so specific that it could like probably do a better job. Like if it
I
had,
think so.
yeah,
You give that shit access to Google, and you're done.
yeah.
Just train an LM on Google.
Yeah, I
We're
have
giving
seen
away
it go
our
round.
We're giving away our secret ideas right now, Galen.
I don't care.
We could maybe formulate a small little company here.
As if I'm gonna do that. I don't have the bandwidth to do that.
Yeah, it's. I think the only thing I'd say is that having once or twice just gone, I don't understand this. Let me bung the error into ChatGPT what it says. It has gone round in circles with some of these things.
Yeah.
So I think there is definitely something. Yeah, it can't. I don't know. Yeah, I've not. Sometimes it is just because you're asking a silly question. You realize you've done something else. But
yeah.
I don't know. I think I still think looking at how ChatGPT has sent me round some really stupid dead ends.
Yeah.
I am still fairly confident that human beings are going to be necessary in computer programming for quite a while.
Yeah. Like until you can somehow marry a deep level like a type level thinking with like the ChatGPT generation, it's just never gonna.
Then you also just get into like language interpretation of like how they interpret your prompts and stuff too. Like it's always gonna need like humans.
Yeah, true.
I think also ChatGPT just has a slight thing of wanting to give you an answer.
Yeah.
So like I mean, once I asked it how to do something, and it just invented a function, and I went, okay, where did you get that function from? And said, no, that function was just an example function. You'd have to go define that. I was like, that was the bit I needed help with, though. Like the rest of this is just the normal gubbins. Like, how do I do that bit? Oh, that's difficult. Yeah, I know.
Yeah, I know that's difficult. I'm asking you.
No, that's actually the best thing I've ever heard from.
I love that.
Yeah, this is just an example function. It's too difficult for me. It's like, I mean, on the bright side though, I think one of the benefits of like this community and like learning Haskell is that like if you can do something in Haskell, it proves you know how to code. They're not just writing like ChatGPT generated slop. Like we were going to do a partnership with another community, and they were like they had like a big ask of us. They were like, oh, like we want like like our developers are so great that we want like a huge portion of like if you guys ever get paid for someone getting hired, right? Because that's how we get paid. If you guys get hired, and they wanted a huge portion of it, and we're like, okay, like so they're coming in like amazing developers, like great. And then we looked at their code, and it was like, this is literally just ChatGPT generated slop. Like this person does not.
It was like
code.
so obvious, yeah.
Yeah. So we said no.
Like when you see code and there's like 17 if statements where there shouldn't be. One of those. Yeah.
It was even easier too. It was even easier too because they had like comments that were like, "That's a ChatGPT generated comment."
Yeah. They left all the ChatGPT comments on, right? Yeah, that's fun. It's like, oh, you're really good at commenting your code. Thank you for describing it so perfectly to me.
Yeah. I mean, it's like
it's when it describes like even the things that are just inherently obvious.
Just like
this
obvious.
is adding the two numbers together.
Yeah, exactly.
Yeah, obviously.
Yeah, obviously.
I'm glad this comment was here.
I wouldn't have known what to do without it.
There's like 4 characters total to like run
Yeah.
the actual logic, and then there's like a 20-line like comment. Yeah.
Anyways, I do have to go.
I
I've got to
should-
get
I was about to say, same here.
food and everything.
Yeah, I haven't eaten breakfast yet, so.
Yeah, I'm going to get pancakes.
Are you actually?
Very different conversation. I'm 6:30 p.m. over here, so I've got to go get actual dinner.
Oh
ready.
yeah.
You gonna get pancakes too, or?
Pancakes
No.
for dinner.
Oh, maybe. Cool. All right, guys.
All
I'll see you next week.
Yeah, see you, man.
Catch you.
Bye, Hillary.
Bye.
Bye, Hillary. Bye, Nick. Bye, Kyle.